So the problem we're going to do for this week is problem number 2, and this is going to be one of the applied optimization problems. So what we're going to read through here is finding an enclosed 400 square foot rectangular garden with shrubs costing $40 per foot on 3 of the sides and a wall costing $20 per foot on the 4th side. We want to find the dimensions that are going to minimize the total cost to do this. So you're going to start with, first thing you want to do is find your constraint equation. So we know that our constraint here is going to be, the area has to be 400 square feet. It's rectangular, so obviously then the area of this is just going to be xy. So go ahead and say xy is 400. So that's our constraint right there. We have to follow this equation in order to get the actual answer. Now we want to set up our actual function that we're going to be manipulating. So we want to find the dimensions of this that minimize the total cost. So our area, or our equation, is going to have to deal with the perimeter of this rectangular garden. So we've got $40 a foot on 3 of the sides. So we go ahead and say f of x, comma y. This is a function of x and y. It's going to be 40x plus 40x plus 40y. Okay, so that's the $40 per foot on 3 of the sides, $20 per foot on the 4th side, so we need a plus 20y. So that's going to be our equation that we're going to need to manipulate. Now, we want to use this constraint to get this equation down into one variable. Now, the reason for that is taking the derivative of this with respect to 2 different variables is going to be a little bit more difficult, so we're just going to go ahead and come over here. We'll solve for one of these in terms of the others. So we'll go ahead and say that y is equal to 400 over x. Okay? Now we take that y and we're going to go ahead and plug it back in here. So we have a new function now that's going to only be dependent on x because we got rid of the y by plugging this y in for these. So we got 40x plus 40x is going to get you 80x. Okay? So we've got a 40y, so plus 40. And then the y is going to be 400 over x, and then plus 20 times 400 over x. Okay? We're going to multiply this through, go ahead and simplify the whole thing, so we're going to say that this is equal to, we've got our 80x still, plus 40 times 400 is going to be 16,000 over x. Plus 20 times 400 is going to be 8,000 over x. And I'm going to go ahead and say that this little piece here is going to be equal to, looks like 24,000 over x. Okay. So now that we've got that as our function, we need to take a derivative of it. So we're going to look at f prime of x. And that's going to be equal to, so the derivative of 80x is just going to be the 80. Then we've got 2400 over x. So that's really, 24,000 over x. So that's really 24,000 times x to the negative 1. We're going to take the derivative of that. So you pull the negative 1, so we're going to have a minus. Keep this, 2400, 24,000, and that's going to be all over x squared. Because it would become x to the negative 2, push it down to the bottom. We want to set this whole thing equal to 0. In order to work on minimizing costs, right? So we can go ahead and manipulate this, and we're going to find that 80x squared is equal to 24,000. Go ahead and divide the 80 across, and you get x squared is going to be equal to 3,000. Yes. So then x is going to be plus or minus the square root of 3,000. So we got 2 answers here, but we really know that it can only be one of these, right? Because x is the length of the wall, so we can't have a negative answer for length. That doesn't make any physical sense. So we can rule that one out and just say that our critical point is going to be x equals square root of 3,000. Okay? So this is going to be one way that will help minimize the cost. The other possible ways that you need to check are the endpoints as well. So those endpoints would be 401 is basically going to be the other endpoints that you would be able to check. So when x is 1 and when y is 1. And then the opposite of that will be when x is 1, y is 400, when x is 400, y is 1. So you need to check both of those as well. When we go ahead and simplify this down, we should, or we'll just do the square root of 3,000. You can plug it back in to the xy equation. So we've got square root of 3,000, y is going to be equal to 400 divided by root 300, root 3,000, sorry. And that's going to be what your y is equal to. Okay, so now that you've got your x, you've got your y, you want to plug doing the 401 into this equation. So if x was 400, then our cost is going to be, you're going to get a 1,600 here, 1,600 here. So what's that going to be? 32,000. You're going to get a 40 times 1, which is another 40, and a 20 times 1, so 60. When you do it that way, you're going to get a cost that's definitely greater than plugging this into the cost equation there. Additionally, the same thing would happen if you're doing x being 1 and y being 400, even with this 20y. So you can plug that in, check that. So the dimensions that are going to minimize it are x equals the square root of 3,000, and y is equal to 400 divided by the square root of 3,000.